Okay. Let's get started. So 5 minutes late. Sorry about that. So setting up the equipment. So this is the recitation for 107.1 machine learning. So I'm one of your TA. My name is Jin. I'm in charge of the Auto Lab. So if you have any questions about the programming assignment, post it on Piazza or write an email to me. Okay. So first I'm going to go over some logistics. And then we're going to do a linear algebra review. So the recitation is going to last for like 1 hour, and after that is going to be the office hour. So feel free to ask any questions. And Jae Young is going to come during this recitation. He's currently in a meeting. So if you have any questions about homework 1, just ask him. Or if you have any question about homework 2, ask me. Okay. So let's get started. So some administrative stuff. So the course website is up on Monday. So hopefully you already know that, and then you can click on that. So for the Auto Lab, so I'll do a short demo later, but it's actually a website that you submit your homework. And for the programming assignment, it's going to auto grade your program, so you can see your score immediately. And the Piazza is actually a forum for discussion, so hopefully you all get into that. So if you are not, please do so as quick as possible. And I'm not gonna enroll you into the Piazza because I see like pretty much everyone is in Piazza right now. So if you are not in, just go and just enroll yourself in. So for the Auto Lab assignment, so there are 2 types of assignment, probably 3. So for regular assignments, there will be theoretical assignments. Usually there's going to be like 2 theoretical problems, and then you just write your answers on a PDF file. The PDF file is kind of, you can generate by like any means you want. You can use LaTeX, you can use Word or any other text editors, or you can scan your handwriting and then you upload that. Just make sure that is in PDF format. Okay. So for the programming assignments, please submit a tarball. Yeah.
Where on the website do we find the LaTeX source file you're talking about?
It's actually on the Auto Lab, so I'll do a short demo later. Okay. So for the programming assignment, actually, you need to submit a tarball. So please like follow exactly the instruction in the programming assignment. So you have unlimited amount of submissions per assignment, so you don't have to worry about like making mistakes or debugging or something. So yeah, I'll post more information about that on Piazza. So let me do a short demo on Auto Lab. So yeah.
I actually have a question. It says that we should prepare the answers to each question separately. Does this mean that for every question you should have a separate answer sheet?
No, just put it in one PDF file.
Right. Like you can still insert a page break after each.
Yeah, you can do that. I mean, you don't have to like squeeze everything into one page, but you can have multiple pages into one PDF file. As long as you submit one PDF file, that's definitely fine. I mean, no matter what's in the PDF file. Okay, so here's actually the Auto Lab. So I guess okay, I can't use my mouse here. What happened? No, it's not working. Okay, I'll use my touch screen anyway. So first I'm going to log out. So click on log out. So first time you log into Autolab is something like this, right? So it's autolab.cs.cmu. Oh, okay, sorry about that. I actually can't change the screen. Okay. Let me see if there's a way to do that. I need my mouse. Sorry, I need to reboot this thing. so you can see that. I don't know. I lost my mouth on the if I use the browser. So yeah. Anyway. I'll do that later. Let's just go forward. So actually, when clicking Auto Lab, it's pretty handy to use. So there are actually two links for homework one for homework 1, one for homework 2. And then there's actually a red button called Submit File. And when you click on that, you just submit a file, like whatever you want to submit. And then it's going to grade for you. Okay. So for the theoretical assignment, we're going to do manually grading. So it's going to take a while after the deadline. But for the auto grading stuff, you can get a score immediately. Okay. So I'll try to do a demo at the end of this presentation. Just don't take more time. You don't have a lot of time. So more administrative stuff. So actually, for the rest of the recitation, it's gonna be we're probably gonna change to this room, and today is just a temporary room. So the TA office hour will be like the 1 hour after the recitation. So if you have any questions, just bring it. Usually during the office hour, we don't debug for the students. Actually, for your question, actually there's a link on the AutoLab called Download Handout. For the problem set 1, if you click on that link, it's actually the LaTeX source file. Okay, just go and check that. So for our team, instructor is Professor Spola. Probably you know that already. So. For TAs, Jae-Young is actually, he'll come in later. He's in charge of all the homeworks. So if you have any questions in general about the homework, please write an email to him. And I'm actually in charge of AutoLab and probably all the program assignments. So yeah, if you have any questions on AutoLab or about AutoGrader, just write an email to me. And Shen Wu, he's currently in China. He will be here in a couple of weeks, and he will in charge of the Piazza. And D is going to work on the project. So if you have any brilliant project ideas, just contact him. And a reminder is that your team formation, like you should email TA about all the members in your team by, I don't remember when, but it should be the end of this month. So please check website and please email to him. Okay, please email to this guy, D. And he'll keep something like a Google Doc or something. He'll probably actually open a Google Doc and let you fill in, and depending on him. So Joe is in charge of the recitations. So you'll probably see her next time or after that. So here are some nice materials for the math. So the first link is is actually a set of videos made by Zico Kotler. Zico Kotler is actually a CSD professor here, one of the best lecturers in CMU. So those videos are very easy, so please take a look at it. And actually, my slides will be posted online later, probably today or tomorrow or sometime. So you don't have to take photos or make notes. So the second link is actually linear algebra review sheet from Jing. So Jing is actually MLD PhD here. He used to be my TA. So actually, you can take a look at her slides. So the third one is actually a very thorough material. Is about everything about matrices. You can find it there. And the last one is a probability review from a guy also from MLD, I think, or I'm not very sure. So just check that out. So today I'm going to cover the linear algebra review. So first, I'm going to go over some basics. So probably very basic, but actually I'm going to go to some more materials in deep that we are very likely to use in this class. And probably I'm going to cover until the matrix calculus. And for the other stuff, you're probably going to see that offline because we don't have enough time to cover that. So, for basics, so for vectors and matrices, so I think probably everybody know what is vectors. What are vectors? What are matrices? So vector is actually a collection of number, and for example, we have vector x, and then we say x1, x2, xn. It belongs to Rn. R means the real, right? So it means for each element in this vector, it's going to be real value. So the vector is of length n. It means there are n elements in this vector, and when we write in this form, it implicitly means that it's a column vector. Right. So remember that. It implicitly means a column vector. If it's a row vector, we will specify that. So for a matrix, so yeah, you already know that. So it's Rm times n. So m means the number of rows, and n means number of columns. So the vector product. So there are two kinds of vector product, which is one is inner product, the other one is outer product. If I go too fast, please stop me. If anything is confusing you, just raise your hand and I can answer your questions. So the first one, inner product. The inner product of two vectors is actually the element-wise multiplication. So the two vectors must be of same length, right? So there are actually a lot of expressions means the dot product of two vectors. You can see this like sharp brackets, UV or U transpose V. Right? So here UV are all column vectors, which implicitly means that these vectors are column vectors. So U transpose V, U transpose is actually 1 times n, right? So if you transpose a column vector, it's going to be a row vector. And row vector times a column vector is a scalar here. Right. So the dot product is usually used as a measurement of similarity. So if two vectors are, the product of two vectors are large, it means like these two vectors are similar. So the outer product, also called the cross product, is actually a matrix. So the outer product of two vectors will be a matrix. And then the difference is that these two vectors do not have to have same length. So for example, if U has length m and V has length n, and you do U cross V, it's going to be a matrix. So we will see that again in the matrix multiplication. Right. So another form is U V transpose. Any questions? Okay. So these are very fundamental stuff. So hopefully you understand that already. So for matrix multiplication, if A is a matrix of size m times n, means m rows and n columns. B is the size of P times Q, means P rows and Q columns. A times B is defined only when n is to P, right? So it means when you do matrix multiplication, the inner dimension must agree. If it doesn't agree, it's not defined. So some properties of matrix multiplication is associative, is distributive, but it's not commutative. So AB is not equal to BA. If AB is defined, BA may not be defined if those dimensions are not agreed. Right. So do not like inverse the order. Just be careful. Okay. So everybody is fine with that, right? So we're gonna go into more details. So we can see matrix multiplication as vector product. So we can see that as inner product or outer product. So for example, if I have a matrix A is n times n, B is n times P, so the inner dimensions agree. So A times B makes sense, right? So let's say AI is actually a row of A, and BJ is actually a column of B. So the result is actually the dot product of the row vector from A and the column vector from B. So this is actually how you do matrix multiplication by hand, right? So for the outer product, for the outer product, we choose the column vector for A, and we choose the row vector for B. So you can see the entire multiplication as a sum of those outer products. If we pick a column vector from A and a row vector from B, and we multiply that, what is the size of that outer product? So is m times 1 vector times 1 times n vector? So what is the size of that outer product? So it should be m times n, right? M times p here, right? So it's m times 1 times p, right? So actually, for each pair of column vector from A and row vector from B, you do the outer product. You have exactly the size as a result. That's A times B. A times B is actually the sum of all those pairs of outer products. Right. Probably the camera cannot see the board, so I don't know. I can do an example. So for the first case, for the inner product case, we write A. Can I see that? On the people on the back? Can I see that? Okay. So for the inner product, we say AI is actually a row of A. Bj is a column of B. Right. So what we do is actually we pick all these pairs, and multiply that together. So the first element of AB is going to be like A1, B1, A1 times B1. So it's actually a row from here and a column from here. Right. So this is actually how you do matrix multiplication. So for the outer product case, let's do A. That's this one. And B. So we select one column vector from A, and then we select one row vector from B. And what's it going to come up with is actually, for example, AI times Bj. The dimension of A is, here is n times 1, right? This guy is 1 times n. So the outcome of this guy is going to be n times n. Right? So the entire A times B is actually the sum of all these pairs. Right. For all the i's and j's, you just pair them up. Okay, so hopefully everyone understand that. So I'm going to move forward. So if you have any questions, just stop me and I will. So the transpose, everybody understands transpose. It's just actually just a switch of rows and columns. So Aij is actually the transpose of Aj. And A transpose is A. This is very easy. And AB transpose is B transpose A transpose. And A plus B transpose is A. You can switch that. It doesn't matter. Right? So rank. So rank is actually a pretty important concept. So a set of vectors, for example, x1 to xn. In this vector, in this set of vector, if there is no one vector can be represented as a linear combination of others, we call this set is rank n. For example, I have like two vectors. For example, say, one second. The first vector is 1, 0, 0. And the second vector is 0, 1, 0. And the third vector is 0, 0, 1. So there is actually no one vector can be represented by a linear combination of other vectors. So it means this is rank of 3. If I do something like 0, 2, 0, it's going to be rank 2. Okay. So a matrix is full rank when the rank is equal to the minimum of its number of rows or the columns. So basically what it means is that if you have a matrix that is Rm times n, so if it's full rank, it means rank A is equal to the minimum of m for n. So for this case, it's equal to m. So what does rank mean? It means there are how many bases you need to represent this set of vectors. For example, in a two-dimensional case, right? If this is a 2D plane, how many vectors you need to represent this plane? 2, right? You don't need 3. So if you have like 3 vectors in a 2D plane, it means it's not full rank, it's low rank, right? So actually you can see this, for example, if you have m smaller than n, it means at most you can have m bases, right? So for this dimension, it's not full rank. So for m, so you can have at most m vectors to represent this matrix. We'll see this later in eigen decomposition, but actually it's a very important concept. So the inverse. So a matrix is inverse only if it's square. So for a rectangular matrix, it has something called pseudo-inverse, but pseudo-inverse is not inverse. And the matrix is invertible only if it's full rank, but there are many other equivalent conditions. We'll see that later. So if A is n times n, A inverse is n times n. A inverse A is equal to AA inverse, and A inverse is again A. And A inverse transpose is A transpose inverse, and you can see that. These are all the properties you're going to use in the future. So there's a homework problem in your homework 1. So it asks like, why is EO conditioned or something? You can like think this, why is this not invertible or something like that. So the trace of a square matrix is actually the sum of its diagonal elements. So the trace is defined only for the square matrices. So if you have a square matrix, and then the trace is actually the sum of all its diagonal elements. And all these are equivalent because they are all these A transpose B and B transpose A, and A, B transpose, and B, A transpose. They all have the same trace because they are all, the value of the trace is equal to that sum. So if you transpose A, it doesn't matter because if you transpose A, you only interchange the rows and columns, and the trace value does not change. Right. So for the other conditions, it's pretty obvious. Okay, so vector norms. So norm, you probably see that in the lecture already. So a norm is actually a measurement of magnitude. So if a norm is big, it means like this vector has a big magnitude by some measurement. So a small norm means like the magnitude is small, right? But the measurement really matters. So this is the family of norms. You can see that as each element, and you do like piece exponential, and then you sum that up, and then you just do something like piece root, right? So for L1 norm is actually the sum of all its absolute value in this vector. So for example, if you have a vector of 3, -2, 1, what is L1 norm? It's just 3 plus 2 plus 1. So it's pretty simple. So for L2 norm, it's actually the Euclidean distance. It's also called Euclidean norm. So for example, for this one, it's just the distance of this vector. Of this, it's actually the length of this vector for L2 norm. So for L3 norm and L4 norm, I don't usually see that, but it does exist. So there are two special norms. L infinity norm. When you try to set P approach infinity, it's gonna give you like the max of that, max of the largest element. You have the absolute value of the largest element. And if you do L1 norm, it's also called card norm. It's actually the number of non-zero elements in this vector. So for example, if you have like 3, 0, 1, 0, and L0 norm is equal to 2. Okay. Number of non-zero element. So non-zero element is also called support. So why is this important? So when we do linear regression, we add some sort of penalties. And if we add L0 norm, it will directly minimize the number of directly minimize the number of non-zero elements in the weights. So we have a sparse solution. Right. So we don't usually use L0 norm because that is not a convex problem. We use L1 norm instead. So it's called lasso regression. You probably heard of that. That's going to give you like a few non-zero supports. So it's a pretty hot topic in machine learning. So if anybody like is confused about that, raise your hand and I'll do that again. Okay. So for here, matrix calculus, this is very important. You're probably gonna do that in the first homework, and in the second homework there is actually a program assignment on that. So for matrix calculus, there are actually two layouts. One is called denominator layout, one is called numerator layout. We're gonna use denominator layout. You can read the wiki page for matrix calculus. There are actually there are actually two columns for each layout. So the denominator layout is actually used as follows. For numerator layout, it's actually you actually switch the rows and columns. So if you end up with a row vector in numerator layout, it's going to be a column vector in the denominator layout. That's the only difference. So for matrix calculus, the function f takes a vector, the function f takes a vector and ends up with a real number. So for example, fy equals to fx. And this x is a vector, Rn. And then this guy is a real number. So it's going to end up with the gradient of this guy is also going to be a vector. So the size of this vector is also Rn. So let's say f is Rn times Rn into R. Partial f partial x is actually partial f, and then partial x1, and partial f partial x2, to partial f partial xn. So this is actually each element in the X array, and then you do this derivative for each element, and then you concatenate them into array. Let me do an example. This is a lot of confusing things. So if x is equal to w1 x1 plus w2 x2 plus w3 x3, right? So we can write that into vector form. So it's actually equal to w transpose x. So w is a column vector. So w1, w2, w3, and x is equal to x1, x2, x3. Right. So you take the derivative of f with respect to w. What you are doing is actually you take f with respect to w1 and w2 and w3. So what you end up with is actually partial f, partial x1, partial f, partial x2, and partial f, partial x3. And then, it's actually not. Yeah, let's do that to w. And then this is going to be x1, x2, 3. So this is how you do the derivative for a real value number with respect to a vector. Okay. So how you do the derivative of a real value with respect to m times n matrix? It's pretty much the same. You end up with a matrix with the same size, right? So for each corresponding element, it's actually partial f, partial like partial w ij in that. So for a vector to vector derivative, you end up with m times n. So you take this is actually y, this is x, and then you come up with like Rm times n. This is the dimension of y, this is the dimension of x. So the derivative will be like partial fi with respect to partial xj. Okay. So this is the easiest matrix calculus. So if you do something like vector to matrix, it's going to end up with a tensor, right? In this course, we're probably not going to encounter this problem. Probably we're going to do that in deep learning, but neural networks model you're definitely going to do that with tensor. But from first half of the course, we don't have to worry about that. So just remember these three forms, and you'll be fine. So for the Hessian is actually a second derivative. So you're probably going to use that in the optimization part. So we're going to go over the Newton's method, and then you're going to compute Hessian. So the Hessian is something like if you have a vector to a real number, you just do the derivative twice. So first time you end up with Rn, and the second time you end up with Rn times n. Right? So first time is a real value to a vector, the second time is a vector to vector. So it ends up with Rn times n. So hopefully this is not too hard. Is it okay for you? All right. So the chain rule. So if you have a composition of functions, and actually, if y is like the outer loop is f1, and then f2, f3, and the most inner loop is fk. So what you have for this chain rule is df1, df2 is at the last. And then for the rest of the step, you just go from the end to the beginning, and then like do the transpose for each step. So this equation is kind of self-explanatory. So there are actually some useful derivatives. So you don't have to do this for all kinds of matrices. So you just remember some common derivatives for matrices, and then you can use them as a formula for like when you do the assignment. So the first one is very useful. A transpose x with respect to x is equal to x transpose A with respect to x, and then is going to equal to A. Here, A and X are all vectors. Right. So if I use uppercase, it's going to be a matrix. If I use lowercase, it's going to be a vector. So the second term is vector times a matrices, and then you take the derivative, it's going to be a matrix. Right. So the second one is a quadratic form. I have it in the slides. So it's going to be A plus A transpose X. If you remember these two equations, you are able to do the first assignment and the second assignment. So, okay. So here's a problem that Alex worked during his class. So we're going to work that again here. So we're going to work out the solution for the linear regression. It's called normal equation for the final result. So the objective function is minimizing this function. This function is actually called square loss. So imagine you have a lot of points, and imagine you have like n data points. And f features. So for this matrix, it's going to be n times f. So n is number of rows, and f is number of features. And w is actually the weight vector. It means the coefficient of this regression. So the w is of f times 1. So it's a column vector, so this means a column vector, f times 1. So if you do the multiplication, it's going to be n times 1. Right? So y is the value that you are trying to regress. So y is the dimension of n times 1. Okay. So for example, if you only have one feature, so it's something like you have a scatter of points, and you're going to fit a line into it. So this is the linear regression. If f is equal to 1, if you have multiple dimensions, you just have like more higher dimension of weights. So minimizing square loss is actually the process of how you're fitting a line. So solving linear regression is actually solving this loss function. So the minimize is actually a process. So actually, for here, you're actually solving for w. So actually, we don't care about the value of this objective function. We only care about at what value of w we get a minimum value. Okay, so take out a sheet of paper and just try to solve that by yourself. So everybody knows how to start with? Yes or no? Right, so just raise your hand if you got the answer. What is it?
X transpose X calibration to X transpose Y.
Yeah, exactly. So I'm gonna do that on board. So you should be familiar with this. So the first I'm gonna do is I'm writing like f equals to this objective function. So what I'm going to do is actually writing L2 norm into a dot product. So this is equivalent to transpose. So y is n times 1, and x is n times f, and w is f times y. So this entire thing is going to be n times 1. Right? The transpose is going to be 1 times n. And this is going to be n times 1. So after that, it's going to be 1 times 1. It's a scalar, right? So this is exactly the loss. The loss is a scalar. Do you have any questions? No? Okay. So this entire thing is going to be a scalar. So just try to check your dimensions if your dimensions agree with each other when you do the derivation. The next thing is you're going to span it. So Q is y transpose y. Minus W transpose X transpose Y. And then is Y transpose XW. And this is going to be plus, you can see that, plus W transpose X transpose XW. Right. So just check that again. So Y transpose Y is a scalar. This is 1 times n times 1. So ends up with 1 times 1. For this guy, W is f times 1. So this is 1 times f times n, then n times 1. This is also scalar. So for this one, 1 times n times f times 1, 1 times 1. The last one is also 1 times 1. So you have 4 scalars doing addition or subtraction, and you end up with a scalar. So if you mess up with the dimensions, just be aware of that. So the next step is taking the derivative. I'm going to erase this. Yeah. So next step, doing the derivative, partial f, partial w. So what is the derivative of the first term? 0, right? There's nothing about w, so 0. For the next term, so there's actually a small trick, but you can do that like directly, but you can see that here is a vector times a vector, xw is a vector, and here w transpose x transpose is also a vector times y. So for 2 vectors, if like A is a vector and B is also a vector, A transpose B is equal to B transpose A. Right? So if they are both vectors. So what I'm going to do here is actually writing them to 1. So this is 2 W transpose X transpose Y plus W transpose X transpose X W. So probably we should already on over to here. I'll do that later. So. Okay. So for this guy, the derivative is minus 2 x transpose y. For the guy here, the derivative is going to be 2 times x transpose x plus x transpose x transpose w. Okay. So what is the transpose of x transpose x? Yeah, it is itself. Exactly. So what we have is 0, 2x transpose y plus x transpose x. That's what we get. So the reason why we multiply 1/2 there is actually we want to cancel out these 2's. So for the original function, there won't be 2's here. So what is the next step? Now we have the derivative. What is the next step? Set it to 0, right? So everybody, can I remove this? Okay. So now we have minus x transpose y plus x transpose x w is equal to 0. So what we have is w is equal to x transpose x inverse x transpose y. Okay. So that's basically, this is called the normal equation. Any problems? Not clear? Okay. So you can see the slides online later. So there's actually a homework problem asking you why this is yield conditioned, or sometimes why you can't do this. Just think about this inversion. And actually inversion is very costly in terms of computation. So when you do when you have very large data set, for example, if you are doing something like using data set from Google, they have like billions of data set. The data set cannot even be stored into the memory. So doing this is impossible. So that's why Alex said in class, you'll never do like this function in MATLAB. But if this is small and this is full rank, you can do that. But if you have a very large data set, doing this is actually impossible. Okay.
Just as a note, when you post this online, your slides have a typo in there in the last equation.
Where?
X transpose X inverse X transpose.
Oh yeah, there should be inverse right there. Sorry about that. Thanks. So I'm probably going to cover the eigen decomposition and then we stop for questions, okay? The rest of the slides will be online. So the eigen decomposition is actually a very interesting topic. So it's strongly related to a topic that we're going to cover in class. It's called PCA, Principal Component Analysis. It's actually how to use a lower dimensional matrix to represent the high dimensional matrix, and you don't lose a lot of information, right? So the formation of eigen decomposition is something like this. It's Q delta, Q transpose. You basically decompose the matrix into two matrices, and the form is Q lambda Q transpose, and A must be a square matrix. It's different from SVD. SVD you can use this rectangular matrix, but for here you must use the square matrix. So for here, each column of Q is called an eigenvector. So the property of eigenvector is that each eigenvector is orthogonal to each other, and they are of unit length. So the length of each eigenvector must be 1. The property of this lambda matrix is actually a diagonal matrix. So all others are 0. And for each element here is called eigenvalue. So it's corresponding to each eigenvector. So the largest eigenvalue is corresponding to the largest variance in that data. So if you have a data set of 2 dimensions and you have like data points scattering like this. So when you do the PCA or like eigendecomposition, you probably end up with the first principal component or the largest eigenvalue corresponding to this factor, or probably the opposite, but it's the same. I mean, pretty much the same. Yeah. And the second eigenvector will be something orthogonal to this one. So by doing eigendecomposition, you actually capture the largest variance in this data set. Right? So if you want to, if you say like you can only remain one dimension, you're only allowed to use one dimension, you're absolutely going to choose this one. So because you remain the most information in this data set. Okay. So if you have a 0 eigenvalue in all these eigenvalues, it means the matrix is low rank. It means there's actually a vector in this matrix can be linearly represented by other vectors. So that's pretty much you need to know about the eigendecomposition. So any questions or other stuff? Yeah?
So the matrix also needs to be symmetric. In that case, Q lambda Q transpose is a symmetric matrix.
Yeah.
So if this eigendecomposition only works, at least in this way you said it is only if A is also symmetric.
Usually,
That is if Q is orthogonal, then Q transpose is the
yeah, I think so. Yeah. Usually we don't work.
Sorry?
Q transpose doesn't have to be Q.
No, yeah, but if you take the transpose of Q lambda Q transpose, then you get Q transpose lambda Q transpose, which is the same thing. So A has to be symmetric.
So you take the transpose of this one. You're gonna have like you do everything inverse. So
There's Q transpose transpose.
yeah, it's actually lambda transpose is
So this means that A has to be symmetric, right?
yeah.
Because I mean, it's represented as a symmetric matrix.
Yeah, I'll check out later, but yeah, you're right. Thanks.
I think in general, the second Q is supposed to be an inverse, not a transpose.
Yeah,
Is the typo.
yeah, I think so. Thanks. Right, so
Isn't it orthonormal? It's a matrix that you transpose is Q inverse. So the Q inverse, the transpose is Q inverse.
inverse, okay, yeah, I'll fix that. Sorry about that. Right, so any questions in general or? So the rest of the slides is about quadratic form and singular value decomposition. You can watch video lectures online. I provide all those links, and make sure that you know what is definiteness of matrices, what is positive definite, what is semi-definite, semi-positive definite, and then remember that covariance matrix is always positive semi-definite. Yeah.
A is equal to Q times lambda times Q transpose. The dimension doesn't work. Dimension doesn't work.
Why it doesn't work?
Because a lambda is 1 by n, say. Okay, then Q transpose is 1 by n.
No. A is actually n by n. It's a square matrix.
Yeah.
And for all those its matrix is also n by n. Each of its matrix is all.
But Q is a matrix, or is a
Q is a matrix. Lambda is also a matrix, and also n by n.
Q is n by n.
So this is n by n, and this is n by n, and this is also n by n. So it works. So it means there are n eigenvectors in this Q. So Q is something like you have QIs for each column, and each column is an eigenvector.
I think that the Q transpose of n is Q inverse, not Q transpose.
Yeah, maybe I'll look at that later. But yes, thanks for pointing out. Okay. So any other questions? About homework or homework 1 or homework 2? Homework 1 is going to due next Tuesday. I think homework 2 is going to be due a week later. Yeah.
Can you derive the linear regression? Can you map it to the nonlinear regression? Is it
nonlinear regression should be. I didn't look at in detail of that problem, but it should be pretty similar. But you just use phi x to like replace x, right? Yeah. So it should be something similar. I mean, I shouldn't work out the homework in the recitation, but yeah, we'll provide the solution after the homework's due. Yeah, one more thing. For the late policy, so there are actually 2 late weeks, for 2 grace weeks you can use. You don't have to give any excuse or anything if you go to a conference or something. You have 2 free weeks to be late. So that means you can use that for only 2 assignments. For each assignment, you can be late for a week. Okay. So if you use the third late week, you should provide something like a doctor notes or something reasonable. Otherwise, it's going to be a 0.
Homework 2, the deadline was 11:59 p.m. on Monday night.
Yeah.
Is that a typo or is that?
Officially, it's due 9 a.m. Right? So, but actually, I extend that to the midnight. So that's actually a very very long grace period. So
Okay.
as long as you submit before that, everything should be fine.
So this is not going to be counted as late or whatever, right?
No.
So we can submit at midnight.
Yeah. Even though you pass like 20 minutes, it should be also fine. I said that as another grace period, but don't do that. Right? So just in case you can't make it for the last minute, you need to use 1 or 2 minutes. Right. So after that, it's going to be counted as late. Okay. So if you have any questions, you're welcome to stay. We're going to be here till 6 p.m. So thanks, guys.
Thank you.